So last time we finished up talking about electron configurations, right? All those S's and P's and D's and F's. And then we also talked about how all the, elements want to be noble gases in terms of their electron configuration. That's kind of ideal. We saw that certain elements would be more likely to gain electrons. They would have high electron affinities. And we would see that some elements would tend to lose electrons. And so we're going to go a little bit further into that today. So we remember that we're going to see that metals are usually going to be the ones that are going to lose electrons, and non-metals are going to tend to gain them, just because of where they are on the periodic table. So if we remember, we saw that group 1 and group 2, 3, 4, 5, or rather 13, 14, 15, 16, 17, and 18. Remember we saw all the valence electrons of these guys? We saw that this was one valence electron. Group 2 had 2 valence electrons. Group 3 had 3, 4, 5, 6, 7, and 8. Oh, that's really ugly. Here, let's go ahead and fix that. Okay, so looking at these numbers, if we look at group 1, remember that things want to get either 8, they want to have 8 valence electrons, or 2 if they're close to helium, because remember helium is a special noble gas that only had 2 valence electrons. If we remember the group 1 stuff, it has 1 valence electron, which means in order for it to resemble a noble gas, it can either gain 7 electrons, or it could lose 1. And which one do you think would be more likely to happen? Yeah, I think it's a lot easier for these to lose an electron. And if they were to lose that electron, what would their charge be? Yeah, so they're going to have a +1 charge, typically, when they form ions. Alright, so let's move on to group 2. If they have 2 electrons, they can either lose 2, or they could gain 6. And so it's going to kind of be the same thing, right? It's a little bit easier for them to lose 2, right? So we're going to see that these will also prefer to lose. And those are going to form +2 ions. So for example, calcium would have 2 valence electrons. It's going to tend to lose both of those and become a +2 ion. Alright, guess what group 3 is going to do? Yes, very good. Yes, they're going to prefer to lose as well. And so we're going to see that those will often form +3 ions. Let's go to the other side. These guys in group 8 don't do anything, right? The noble gases are already noble gases. They don't need more electrons, and they would definitely not want to lose any. All right, they already have that magic number of 8. Alrighty, so if we look at the ones in group 17 then, the halogens, they have 7 valence electrons. Are those ones going to be more likely to gain 1 or to lose 7? Yeah, they're going to gain 1, and if they do so, what's their charge going to be? Yes, exactly. So those are going to be -1. And we're going to see the same thing is going to happen in group 16 and group 15.
Pero así jugando, porque obvio pusieron a estudiado de nursing.
Alright, Tyrone, you're gonna get muted. Sorry, my friend. Okay, cool. So, we're gonna see that these guys are gonna prefer to gain, and they're gonna get to a charge of -3. Now, we have the question of stuff in group 14. We say that they have 4 valence electrons. They can gain 4 or lose 4. What do we think they're going to do? It's an interesting idea. All right, I'll tell you. So they can go either way. So they can go +4 or -4, depending what they're mixed with, basically. Ah, a visitor has come. Oh, come here. Come here, buddy. Oh, he's hiding under my desk. Okay, maybe we'll get to see him a little later. Okay, cool. So we're going to see that these groups on the periodic table, because of their electron configurations, can give us information about what preferred ionic charges they're going to have. All right, again, because things are going to tend to be wanting to be noble gases, they're going to potentially gain or lose electrons to do that. Alrighty, so let's do some practice. Okay, so again, this is going to all follow that kind of periodic table sign of way. We're going to see group 1 stuff is typically going to lose an electron, lose 2 electrons, lose 3, could go either way, gain 3, gain 2, gain 1, and don't do anything. One thing special about hydrogen, by the way, can gain or lose. Because hydrogen up here, has 1 valence electron. To become a noble gas like helium, it can gain an electron. We're also going to see it can lose its electron too, and that'll be just as good. So hydrogen can either be plus or -1, but we'll see that in a little bit. Alrighty, so cool. Let's do some practice. I'm going to write out some elements here, and I want you guys to tell me their preferred charges. How about this one? And this guy, and that one. Okay. Have fun. 8 elements. I want you guys to tell me what their charges should be. If they're going to form ions. So go ahead and take a minute or two to work on this. Not negative, Robert. I don't know if that was a hyphen or a negative, so... Okay, it is not negative, so Elza is correct. Yes, it loses them. I'll write it in a different color. Why -1, Robert? I like Meridy's answer. So Robert, find nitrogen on the periodic table and see how far away it is from a noble gas. Good. Looks good. So far, so good. Mm-hmm. Yep. Oops. Yep, that's right, Zoe. Actually, I shouldn't have written the -1, just minus. Okay. Yeah, typically, Samville, we want to write the number first. It's just convention the way we do it. Um, I can't quite tell you why we do it that way, but we all do it that way. So you'll want to do the same thing. Okay? Alrighty, cool. Anybody have any questions on these? Correct. So we're going to see that if it is in group 15 or higher, it's going to gain electrons, and it's just going to gain enough to become that noble gas. If it's in group 13 or 2 or 1, it's going to lose electrons to reach that noble gas section. So remember, we could go, yeah, exactly. That's exactly right, Robert. And so we're going to see that nonmetals tend to be on this side, and nonmetals are typically going to be our negative ones. And we're going to see metals are going to tend to be on the left side, and so those guys are going to be more positive. Aha, very good question, Marissa. So if you remember way back when, I gave you guys that chart with the polyatomic ions. It also has some of the information on transition metals. I'm going to give you some examples, but by any means you do not have to memorize these, okay? So iron typically is found as 2+ or 3+. Copper is often found as 1+ or 2+. Okay, manganese can go 1+, 2+, 4+, 6+, or 7+. We're going to see that these transition metals do all sorts of crazy things. And so we're not going to memorize all of these charges. These are just examples of what things that can happen. We're going to see that instead we're going to have a special way to talk about transition metals that we'll talk about in a little bit. All right, for now, there are 2 transition metals that we do want to take care of. 2 transition metals in particular, which you must memorize, are silver and zinc. I will say this, memorize these. These guys are special in that silver only goes 1+ and zinc only goes 2+. All right, fun way to remember that. Periodic table, as always. We find aluminum here. We know aluminum, being in group 13, will have a charge of +3. Zinc, diagonal down from it, is +2. And diagonal down from zinc is silver, which is +1. So 3, 2, 1. Oh, I'm sorry, this mirror image thing is just killing me. But 3, 2, 1. That could be one way you could remember it. Okay, so you will want to learn that zinc and silver have fixed charges. They do not take anything besides those 2 charges, okay? Cool. So, now that we've talked about these charges, let's see how we're going to put them together. Alright, so say we had this guy and that guy. In order to make a compound between ions, things must be balanced. That means pluses and minuses, okay, have to be balanced. Because we're going to see that all compounds are going to be neutral. They're not going to have an overall charge. So if you wanted to put sodium and chlorine together, the ions that they've formed, we're going to see that we need 1 sodium and we need 1 chlorine. Right? Because one of them is 1+, the other is 1-. If we just put those 2 guys together, they'll cancel out. And so we're going to end up getting this guy. Okay, where we know that the first element is our positively charged ion, and the second one is our negatively charged ion. Okay, but what if they're not the same size, or same charge? Or rather, same but opposite charge. Let's have a look at that. What happens instead if we have sodium and sulfur? What do we think is going to have to happen here for us to make sure that this compound is balanced? Yeah, we're going to need 2 sodiums, right? Yeah. So we need 2 sodiums for just 1 sulfur. Alright, and that will combine to become Na2S. So this subscript underneath, next to the sodium, indicates that there are 2 sodium ions there. Each of those sodiums is 1 plus. So overall, the positive side is 2 plus, because we have 2 sodiums. And our negative side is 2 minus, and therefore it is balanced. Okay, hopefully that's okay. Let's do one a little bit more complicated. This is called charge balancing, by the way. Let's do calcium and phosphorus. I want you to tell me the charges of these 2 ions. Just as practice, of course. Can't hurt to get more practice. Yeah. Looks good. Great. Very nice, guys. Okay, so this one's a little bit more complex. We don't have a very easy solution here. We see that if we put 2 calciums, we're going to have 4 plus overall. And that 3 minus, still doesn't quite balance out with that, right? So we're going to have to do a little bit of math here. Hopefully you remember way back when you studied, let's see, what's it called? I think the least common multiple, I think that's what it is. It's been a while since I've done Algebra 2, so that's okay. We're going to want to see that whenever we have, charges that don't nicely go together, we're going to want to multiply them together to find out what a nice balance would be. So if we see that 2 times 3 is 6, right? We're going to see that we're going to have 6 positives and 6 negatives to balance this out. The reason for that, again, because they're kind of not easily fixable, we're going to need to have the multiple of them. Yeah, Tiffany, this looks good. So we're going to need 6 plus and 6 minus. That's the least common multiple. And so we have to think, how many calciums are we going to need to get that 6 plus? We're going to need 3, right? And same thing for the phosphorus. If we need 6 minus, we're going to have 2 of those. And so, putting that together, we're going to get what you guys have already said, which is Ca3P2. All right, I will show you guys a shortcut for this. We see that, I'm going to just do it on the side here. If we take this number, we can put it with calcium. And if we take this number, we can put it with phosphorus. And if we do that, we should get Ca3P2. Just moving these charges crisscross down, that will automatically do the work for us. There's always a shortcut, yes. But there is one thing that we have to be aware of. Okay, in the next example, we'll talk about that. Alrighty. how about we do something that you guys, well, I guess didn't quite do, but we're going to do in the lab before things close down, was make a compound between magnesium and oxygen. What do we see is going to happen here? So technically, if we do our crisscross... Yeah, you guys are ahead of me. Good job. If we do our crisscross, we'll technically get Mg2O2. But, as you guys are already saying, because these are the same, they're both divisible by the same number, we want to reduce, which lets us get to MgO. Okay, so that's just one thing you have to keep in mind when we're working with the crisscross method. However, if you use the other one where you're kind of counting how many are going to be needed, you'll see that it's 1 magnesium, 1 oxygen, and you can do it that way too. Okay, and of course, if you just noticed, hey, they're the same charges, that is always going to cancel out. That's, totally acceptable also. All right, so far so good. Any questions on this sort of thing, charge balancing? Okay, so great. So far we've only been working with things that only have one charge. All right, so let's go charge balance with some other things. We're going to see that between these ones that have one charge only, like magnesium is only 2+, oxygen is only 2-, there's only one thing we can make with them, and that's MgO. There's nothing else we could do. However, if we have something like iron, which could go either way, let's go ahead and combine both of these with oxygen and see what happens. What's going to happen in the first case? Yeah. We're going to get FeO. Which, of course, as we all know, is ugly in Spanish, right? Feo. There's your lesson for the day. And the other one? Absolutely right, Tiffany. Very nice. Fe2O3. And Tiffany got that from either crisscrossing or just doing the least common multiple. And she was able to come up with these compounds. So we see because iron could take multiple charges, it could make different compounds with oxygen. And so we're going to see that later when we talk about naming these things, we're going to have special names to talk about the first case, FeO, versus Fe2O3. All right, so we'll get into that. Let's talk about naming then. Any questions so far? Yeah, we'll get into those too, Robert. So right now, we're just going to work with these kind of binary things. We'll get into polyatomic ions in a little bit. All right, Cassidy's typing. Let's see what she's got for us. Okay, I'll let her type. In the meantime, okay, let's see. I guess most recently what I had said was that because iron can have different charges, that it's allowed to have different charges, it could make different compounds with oxygen. We're going to see that while magnesium and oxygen put together can only make that one compound because they have fixed charges, iron has a variable charge. And as a result of that, it could make multiple compounds with oxygen, and we're going to have a special way to name that later. Okay, so here is our first case of naming. We're going to have metal, non-metal. All right, I always like to give these cases with something you already know. You have seen this compound before. What is the name of this compound? Yes. I prefer Robert's answer in this case, Samuel. While you are technically correct, yes, we're going to do chemistry-wise. So, we're going to see that this one we're going to leave as sodium. And this one we're going to have chloride. Okay, we're going to see that when we have a metal-non-metal, we're going to end that with the suffix "ide," just the way that we're going to talk about it. Because if we just talk about these guys, we're going to see that this one is called a sodium ion, and this one is called a chloride ion. Okay, and so if we are going to put these names together, we're just going to get rid of the word ion because that's redundant. So to put them together, we're going to put sodium and chloride. Okay, so notice that the root of this was chlorine. What we did was we dropped that kind of last section of it and replaced it with ide. Okay, and we're going to do this for every nonmetal that is part of an ionic compound. Alright? We're going to see that the metal, in this case sodium, is not going to change its name. So sodium chloride is a result of sodium ions and chloride ions coming together. Okay, so let's do this one now. Alright, remember, since this particular compound is made with Ca2+, add F-, you're correct, Robert. We don't need any sort of numbers in here. We're just going to say, I like your answers, guys. We do not care about this 2. Okay, and since we know that fluorine has to be a -1 ion, the fluoride ion, and calcium has to be +2, the only way that calcium and fluorine can get together is as calcium fluoride, which you guys are absolutely correct in saying. By the way, Robert, there is a U you have to worry about. No, a U. Ha 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 ha. Okay. Notice again that we are going to end our name with the suffix "ide." Doesn't it? The periodic table should spell names for you. Okay, cool. Well, sorry, Robert. Go online, perhaps. Okay, let's do another couple of them. Since you guys are so good, how about we do this one? And let's also do very nice. Great. Not quite, Robert. Not in either case. Notice that we always want to end with "ide" here. Okay? We're taking aluminum sulfide. Alright, the reason for that, Robert, is we have special things. Remember, this guy is sulfide. Okay, the element by itself that has a charge, it takes that "ide" ending. However, we know the first 2 of these already have special names. We've already studied them. Remember, this one is sulfate, and this one is sulfite. Okay, and we're going to see that this is why the spelling is going to become important. Because if you mix up sulfide and sulfite, you could kill someone. All right, sulfides are particularly toxic, whereas sulfites are not. So, yeah, not the best thing to do. So we see that in this aluminum example, we do not have SO4 or SO3. So we're going to name this with sulfide, because we have the S2 minus ion present there. All right, is that okay? So all we're doing is taking the name of our metal and putting with it the name of our nonmetal ion, which should end in "ide." All right, is that okay so far? Good, good, good. Okay. Oops. So let's look at case 2. Adding in polyatomic ions. This is, in fact, the easiest way to name things we're going to see. Alrighty. So, how about if we had something between these two? How are we going to charge balance this? Yes, yes, you're ahead of yourself. Charge balance it for me. Yeah. You guys are absolutely 100% right. Put these together, we should get Na2SO4. The name of this, as we remember, was sodium. And the name of this guy we saw before is sulfate. And so, this becomes even easier for us to name. We just call it sodium sulfate. You just take the name of your metal, take the name of your polyatomic ion, put them together. That's it. Okay, there is a space in between them. Nothing is capitalized, just, standard everyday writing. Alrighty. So, how about I give you something a little harder to charge balance? How about we do... Yes, let's do this one. Okay, let's talk about charge balancing this monster, and then we'll get to naming it after. You guys are so good. How did you know that? Are you cheating? You probably have the answers written on your hands. Yeah, that must be it. Yeah, it has to be. You guys are absolutely 100% correct again. Good for you. So, if we think about this, we need 2 OH minuses. Yeah, I'll explain that, Robert. Okay, so if we want to think about that, we're going to need another OH minus. Right? So if we're just imagining that this calcium is next to these OH minuses because they're going to charge balance each other out. If we were just to write that, this means 1 calcium, 1 oxygen, and 2 hydrogens. All right, however, we actually need 2 oxygens as well. And we're not going to do something crazy like that. That's just a little, get that away. That's disgusting. We're actually going to write this using parentheses to indicate that we have 2 hydroxide ions there. So anytime you have multiple polyatomics, ions, use parentheses. Aha! This is one of them. This is the essence of anger, everyone. He hates everything and everyone. So, yeah. Yay, the creature. That's his name, by the way. Say hi, creature. Yeah, you should be terrified. Yep, creature. Or if you really want to be nerdy, it's creature in... Oh, shush. Okay. Okay, he's on the couch now. So, yeah, he's a monster. So yeah, he's just an angry old dog. So yeah, he's very feisty. So there you go. Okay, there's our dog of the day. Oh, of course. In fact, the day I met him, he bit me. That was like the very first thing that happened. Yeah, he's bit me quite a few times. So yeah, yeah. So, shut up, creature. Okay, so it's technically creature spelled Harry Potter way. Yeah, exactly. Okay, hold on. Now he wants to get off the couch. Come on. Okay. You'll have to forgive him for a second. He's gonna go find a place and he'll go to sleep. So, yeah. Let's see. Yes, you get a bonus. Pog, pog, pog. Okay, poggers. Cool. So, anytime we're going to need multiple of a polyatomic ion, we are going to use these parentheses. Okay, by the way, what's the name of this? Yes. These ones, like I said, are nice and easy to name when we have these polyatomic ions. Alright. So far, so good. I'm going to give you two I want you guys to do, okay? In fact, these are easier to name than they are to charge balance. Go figure. And let's go ahead and do... Ooh, how about this one? No. I want this. Okay, Ingrid, try disconnecting and reconnecting again. Or you can try like closing Discord and reopening Discord. Sometimes that seems to work. You're right, Melissa, by the way. Very nice. Very nice, Robert. Okay, sounds good, Ingrid. Robert, a couple things just to point out. Technically, you are going to want to capitalize the N, the H, the C, and the O. Technically, you have a 0 there. So I'm just saying, like, if it were a computer thing, you would probably get that wrong. Even though, like, you have the right formula. Like, I don't want you to fail Gellert's lab because of that. So, so yeah. Okay, cool. So you guys are absolutely right once again. By the way, what's the name of the second one? I see we have a name for the first one. Yes, almost. Very, very close. Yes, Anvil has it. So Melissa missing an M there. So unfortunately, like, these things matter. So okay, cool. So Ca3 PO4 2. All right, and then we have NH4 2 CO3. Okay, and we saw this was calcium phosphate, and this was ammonium carbonate. Wait a second. Speaking of all this misspelling, why hasn't Manuel typed anything today? This is a bit suspicious. So arpin, that's just the name of the polyatomic ion. So this one is called ammonium, and this one is called carbonate. So those are just from that chart that I gave you. That's why I had you guys memorize those, is because if you can imagine learning all this naming stuff and then having to learn your polyatomic ions on top of that would get very, very crazy. So that's why. Is this okay? Is what okay? Oh, I see. That's wonderful. Oh dear, someone's crashing the pots and pans. Okay, cool. Let's see. Yeah, that'll be L. I'm gonna mute you, L. Okay, for now. Okay, cool. Alrighty. I'm going to throw you guys into the deep end now. We're going to now tackle that question of the ugly iron and the rusty iron. Alright, we had these two things. I'm going to tell you how they're named. This one is going to be, if I can spell, iron 2 oxide. And this one, yeah, these are special cases. Well, we're going to see all the transition metals are going to be special cases. So these are technically the names. Yes, Melissa, we also have special names for these. This would be ferrous oxide, and this would be ferric oxide. That's true. These are the old ways. These are the new ways. So numerical notation is the ideal way to do it. That is what the International Union for Pure and Applied Chemistry says, the IUPAC. However, in old things that you see, people will still refer to stuff as ferrous or ferric. But those names are, I mean, while they do mean the same thing, like they're just kind of old. So, just not what people use anymore. So, okay. So we're going to see that this number in parentheses is going to be, we're going to have the metal's name, we're going to put the metal's charge in Roman numerals, and then non-metal with "-ide" at the end. Yeah, exactly. So, Tiffany, sometimes they say that, but typically, medicine kind of does its own thing. Like, they use GM for gram, which kills me. But, yeah, I don't know. You'll probably still see ferrous sulfate around in that. And when you see Gellert's stuff, he often writes ferric and ferrous as well. So I'll just make this a little bit bigger. So, okay. So this is how we're going to name them. All right. The book has a list of all these special names: ferrous, plumbus, cuprous, all these like old names. You do not have to memorize them, but it would be a good idea just to know what they are. Okay. So how we are going to name this? We're going to have the name of the metal, the metal's charge, which was in Roman numerals, correct arpin, and then the non-metal with the "-ide" prefix or suffix. So we're going to see that we're going to use these. So this will be for any metal with variable charge. Okay, that means not group 1. Not 213 or Ag or Zinc. So anytime we have something in group 1, 2, or 13, for example, sodium, magnesium, or aluminum, that's 1, 2, and 13, silver or zinc, these guys have fixed charges. Okay, all the other metals are going to have variable charges. Okay, so if it's a fixed charge, we do not need to indicate with the Roman numerals. However, any time that we have one that does have a variable charge, we're going to have to indicate what that charge is in parentheses using Roman numerals. Okay, let's do a few examples of this. And let's also do, how about, yes. Okay. Just gonna put a little line there. They're different problems. Okay, both of these metals are not in groups 1, 2, or 13. So they are going to have variable charges, so we're going to need to put those charges into parentheses when we name them. Okay, first things first, we're going to charge balance. So what is the first one going to be charge balanced? Very nice. Very nice. And now what are the names of these things going to be? Yes, Robert, I can talk about that. So, Samville, you are technically right, but you want to do what Arpin and Elza are doing. You're going to want to put those numbers in Roman numerals. Oh, okay. Okay, I will write those for you. Oh, so for on the computer and stuff, you just use an I. Yeah, I's and V's and stuff. Yeah. Nobody has computers that have Roman numerals like built in, so okay, cool. So we're gonna see Elza, I kinda like that, but Roman numeral 4 is not that necessarily. It's IV for yeah, exactly. So cobalt 2 chloride. These will be capitalized, and this is titanium 4 oxide. Okay, so let's go and look at this balancing of the titanium 4 oxide, since there was a question about that. How about green today? So if we have titanium 4, Robert, which way do you like doing, the crisscross or the like counting them? Okay, cool. We'll crisscross them. So we technically get Ti2O4. However, we see these guys are both divisible by 2. And so we should divide them both by 2, so we get TiO2. Yes, you have to reduce any time they are capable of being reduced. Okay. Shall I trick you with one? Yes, I think I should. Okay, good. So, ooh, this is gonna be nasty. Okay, but again, the more tricks we do during class, the less likely you are to fall for tricks later. Yes, it really does say CU. CU plus. Put these guys together and name it for me, please. I like Melissa's answer, Robert. Melissa did not fall for my tricks. So, technically this would be cuprous oxalate, but I like Marissa's answer a little bit better. I want to not use those old ones. Melissa, that is not quite correct. It is the Russian name, yes. So we're going to see that pretty much everywhere. You're gonna see ferrum and all that stuff. Yeah, Robert, we're not going to simplify it. I'll talk to you about it. Why? And Melissa, it's not chromate, it's oxalate. Chromate is this. CrO4 is chromate, 2 minus. We're actually using oxalate here. I know, it's a 2 instead. Very similar, very common mistake. Don't worry. Better to make mistakes here. It is good to fail. Failure will be a good teacher. So I very much agree with whoever it was. Let's see, it was Melissa, yes. Cu2, C2O4. Let's think why we're not going to reduce this. I'll write it here. Copper 1 oxalate. That is the name. Okay, if you were really crazy, you would say cuprous oxalate, but again, I'm not going to make you memorize those. Okay, so why don't we reduce these? Anybody have any idea? Well, Melissa, you didn't. Maybe you can tell us why? Exactly. Yeah. So, yes, exactly. So, I like you guys are kind of having the same answer, which is awesome. So, oxalate is kind of one thing by itself. It must be C2O4. Okay, so we cannot change the polyatomic ion. We can change the subscripts when they're not polyatomic ions, like these ones were. These ones were not part of polyatomic ions, so we can reduce those. However, let's see. We're never reducing subscripts that are part of polyatomic ions. Okay, never reduce those. Okay, if you were to have, for example, let's see what's a good one. No, that's not a good one. No. Forget it. Okay. Another example, if you were to have something like Cu2 plus and OH. No, not OH. Let's do sulfate. If you did crisscross, you would get Cu2, SO4, 2. These guys are not part of polyatomics. So we can reduce. And you would get CuSO4. Correct. We can mess with the part that comes from the charges, but stuff that's part of it we must keep. Okay, so oxalate, because C2O4 is essentially what oxalate is, we can't get rid of that 2 and 4. Alright, but this 2 that was outside of sulfate, it just tells us there are 2 sulfates. And so we can reduce the number. 2 coppers and 2 sulfates, we can make it 1 copper and 1 sulfate. That would be okay. By the way, what's the name of this? Yes. Homework 2 is still due tonight. Hopefully you guys will have submitted some of that. Yes, yes, yes. Very nice. Oh, what am I doing? Very good. Do we have questions so far? We're going to take our break in just a minute, let your brains rest. We're going to do more practice of this, and we'll talk about our last way of naming things once we get back. Okay? So let's go ahead and break until 4:40. And